Hi, my name is Thatchaphol Saranurak, and this is a work about deterministic algorithm for balance cut with many applications. So to motivate this work, let me start with applications. The first one is about dynamic connectivity problem. This is the main motivation and one of the most fundamental dynamic graph problems. Here you are given a graph which undergoes some edge updates. You just want to check if the graph is still connected after each update. It has a long history and people get stuck at root n update time for a long time. People keep asking if we can make it deterministic, we can get deterministic algorithm below root n update time. And eventually in this work, we can do it. Enter little one instead of root n, not Las Vegas or Monte Carlo. There are many other applications to make flow, electrical flow by partial matching. This problem, people know less fast deterministic algorithm and people get much faster randomized algorithm that are Monte Carlo. They can make a mistake. With this work, we de-randomize all of them without sacrificing running time. So that's nice as well. It turns out that the core subroutine of all the application I mentioned is from this subroutine called balance cut or prune. Before defining this, I need some definition. Let's say that the S is a cut in the graph on the smaller side. We say that S is phi sparse cut if the ratio between the cut size and its volume, which is the sum of the degree, if this ratio is less than phi. All right, that is this is relatively small. The cut size is relatively small compared to its volume. And we said that G is a phi expander. This graph is phi expander if it has no sparse cut. And in this talk, many times I just said that the graph is an expander. I mean that there is a 1 over n to little 1 expander. So it doesn't have very sparse cut. It's quite good expander. Now let me define this subroutine, bow cut, balance cut, or prune. I denote it by bow cut prune. It's given a graph. Then you need to return a set S on the smaller side such that one of the two cases must hold. The first case is when in the balance case, S must be sparse and the volume of S is like a 1/3 fraction. So the cut is balanced. So this is both sparse and balanced. On the other case, S can be small. It can be even empty, or otherwise we need that the number of edges crossing the cut is small, like a 1 over log square fraction. But the most important thing about this case is that the complement of S is an expander. If S is empty, then it says that the whole graph is an expander. Otherwise, it said that by removing some small set, the remaining part of the graph is an expander. Then what we show as a main theorem is that there is a deterministic algorithm for solving this problem in almost linear time when the quality phi here is not too bad. It's like 1 over subpolynomial factor. And this is really the core thing that implies everything, because I will be quick here, but if you have a graph and you recursively apply this algorithm to the graph, if you get balance cut, you recurse on both sides. If you get prune, you recurse on the smaller side. You repeatedly doing this, what you will get is that it will induce a partitioning, vertex partition of a graph such that each part is an expander and there are few edges crossing each part. This is exactly expanded decomposition. And from this, you will get all application I mentioned before. You can see this talk in this link, my talk in this link that says more how to get all the application from expanded decomposition. But so in this talk, we will focus on the core subroutine of bow cut prune. This is we will focusing on. Now, Without loss of generality, I will assume that the graph have constant degree. And the plan is the following. First, I will tell you that there are two-way reduction between the subroutine of bar cut prune and the process called cut matching game. There are two-way reduction between them. But this will give some chicken and egg situation. And the key idea is how to resolve this chicken and egg situation. This is a key idea here, but to explain this, I need to tell you in high level about the reduction on both ways. Let's start with one way, the first way. Assuming that you have bar cut prune subroutine, how to get cut matching game. So what it is, this cut matching game is the process for building an expander from few adversarial matchings. Let me be more specific. It's a process where you start with an empty graph, and then there are rounds. In each round, you need to choose a bisection A and B that divide the graph into two sides equally. Then there will be adversary that choose some perfect matching M that cross this bisection. And then you add this perfect matching into the graph. And then you choose the next bisection. The adversary then choose another perfect matching that you have no control of. It can be adversarial and so on. And you add this. And the goal is that to choose this each bisection cleverly so that within a few rounds, X become an expander. It turns out that you can do it fast. Each round you can choose a bisection in almost linear time so that after log n many rounds, the X become an expander. It's known how to do this in randomized setting or deterministic and slow, but we can do it fast and deterministic, assuming that we have bar cut prune subroutine. The algorithm is so simple. Just look at the current graph X, run bar cut prune subroutine and get the cut S. Choose A to be any set that contain S. That's it. That's the algorithm. I will not go over the analysis because it is really from, the idea is from Carnegie et al. In this paper. Although they don't define bar cut prune, we define it and it makes everything so simple and it fits together very well. So basically, to summarize, let me denote T cut matching for the total time to choose all the bisection so that after a few rounds, X become an expander. This time is can be done just by calling bar cut prune log n times in each round, basically. In each round, we just call bar cut prune, and that's how we get this. Now we show another direction of the reduction, how to get bar cut prune from a cut matching game. So to do this, I need a notion of embedding. Let's say that G and X are graphs. And I said that P is an embedding of X into the graph G if first P is a set of paths in G. And next, for each edge in X, there is a path. For each edge UV in X, there is a UV path in G. That is from P. And I said that this embedding has contingency if for every edge in G, it is used by at most C path from P. And if this P exists, then I said that X can be embedded into G with congestion at most C. All right. So now it turns out that if we want to find an embedding of a matching in the graph, this can be done just by using single commodity flow. How? Suppose you have a graph G, black graph, with a bisection A and B. you can first set the capacity of every edge to be C, and then add a dummy source S, connect it to everyone in A with capacity 1, and also similarly have a dummy sink T, connect it to B, to everyone in B with capacity 1. Now, consider the value of ST max flow in this graph. And I denote this by flow from A to B. So suppose that you can send, observe the following. Suppose that you can send the flow, the max flow is kind of full. Like you can, every node in A can send 1 unit of flow to some node in B. So the flow is full, is of size A. This is the same thing as saying that you can embed some perfect matching between A and B, call it M. You can embed this perfect matching into G with congestion C. The congestion C comes from the fact that you set the capacity of every edge in G to be at most C. All right. So now consider the following. Suppose that I set the capacity, look at this graph again, and if I set the capacity to be like quite large, log square n, say, then there are two cases that we can exploit. If the flow is small, if the flow in this graph, is the ST flow in this graph is quite small, quite smaller than A. What does it mean intuitively? It means that there are so many guys in A that cannot send to B. So the flow kind of got stuck, even if you allow the capacity of HH to be quite large. What it means is that it can be shown easily that once you have this situation, it means that you can find some cut that is sparse and the volume is quite large because so many guys got stuck. And because it got stuck, that's why the cut must be sparse. This needs some proof, but the intuition is kind of clear. And that's why we say that we get kind of quite balanced cut, not that so balanced, but it's quite balanced and it's sparse. This is kind of what we want actually. And otherwise, the flow is large. So almost everyone in A can send to some guy in B. What does it mean? It means that you can embed near perfect matching between A and B, call it M prime, into G with small congestion. The logic is just the same as before, but now because not all guy can send the flow, so it's just near perfect matching. Even more, we can also say that actually you can embed a perfect matching M by adding some fake edges here so that M prime become perfect. You can embed a perfect matching M if you just add the same fake edges into G. For each purple edge, you can just embed it into this purple edge. You just add this purple edge in G. So you can embed perfect matching M into G by adding some small number of fake edges. Note that these fake edges must be small because M prime is near perfect. So F must be small. So what do we have here? Just let me conclude. By running single commodity flow, we can either find a balance cut or embed a perfect matching into the graph with using some few fake edges. So this will be useful for us. Now let me describe. Now I'm ready to how to describe like the algorithm for Bao-cut prune. There are several steps. The first step is to start with a template from a cut matching game. Here you start with an empty graph. There are log n many rounds. In each round, the cut player chooses a bisection. Then an adversary chooses a perfect matching crossing that bisection. You add a matching into the graph and repeat. This is just a template from a cut matching game. The second step to describe the algorithm is to specify the adversary. And to specify what is this adversary, I will just use a subroutine I mentioned just before. That is, given as bisection A and B, I will check the max flow value between A and B. If the flow is small, then we get balance cut and we are done. Otherwise, the flow is large, and then we can embed a perfect matching into G with some help of small number of fake edges in this round. So we repeat this for log n times, right? And if the flow is small, we got a balance sparse cut in G, and we are kind of done. Otherwise, if we don't get this case at all, then we can conclude that X must have become an expander already, because this is really just a promise from a cut matching game. After log n round, X must be an expander. And moreover, what do we have? We have that we can embed X into G plus F, where F is just a union of all fake edges from each round, and F must be small because in each round Fi is small. So we can embed X into this graph with small congestion, where log square is from the congestion from each matching, and because there are log n many matching that comprise X, then this is a congestion here. So we have that X is an expander that can be embedded into this graph. It can be shown easily that it must be the case that, and the congestion to embed is small, for embedding is small. So if you can embed any expander into any graph with small congestion, you can conclude that that graph must be an expander, and we use this fact. And now G plus F is an expander. From here, you can conclude that you can work some more and conclude that you get a prune case. To see a bit why this is the case, suppose in the extreme case that F is empty, then G itself is an expander. So it means that we don't need to prune anything out, right? And the whole graph is an expander already. Otherwise, if F is small, you can still use something called expander pruning and prune some small set out of the graph and say that the rest remain an expander. So we either get a balance cut or prune case. It's not like exactly the constant is not exactly the same, but this is the high level how to get balance cut or prune. Let me rephrase what I just told you. We just show that to solve balance cut, bound cut prune subroutine, you can reduce it to cut matching game, because in each round you can try, given a bisection, you will try to embed a matching by finding a single commutative flow, and we try to embed matching for log n rounds. In each round, the bisection is chosen by a cut player. If one of the round have small flow, you get a balance cut and you're done. Otherwise, you have that the graph X is an expander after log n rounds, and you can embed an expander into this graph G. So it means that this graph G must be an expander, and with some more work, you can get a prune case. And the time here is the running time is just the time to compute flow in each round. That is to embed a matching. And this is just this can be done in linear time using some dynamic shortest path. The other time is just the time to choose the bisection. But by definition, the total time for choosing bisection is denoted by T of cut matching. So we get this inequality. And so you can see that with these two inequality, from cut matching, you can call Baukat prune. From Baukat prune, you can call cut matching. These are good, but it's a chicken and egg situation. The size of the instance is not reduced. And this brings us to the key part, the key idea of this work to resolve this situation. The key idea is the following. Instead of trying to solve Baukat prune, instead of trying to embed the one big expander into the graph, and then you need to solve a cut matching game, you need to find a bisection in this this big graph X, which of size n. We don't want that. You instead want to reduce the size of the instance here. So the idea is the following. You divide the graph into k parts, and then you try to embed smaller expander, k of them. Each of them has size n over k. Embed k of them into each part simultaneously. What does it mean? It means that in each round in the cut matching game, you try to find k bisection in each of the x here. The time to do that, the total time to do that is to call x many cut matching game in smaller graph. Once you have a bipartite, a bisection in each x, you need to embed a matching crossing each bisection into the graph. This will correspond to k commodity flow problem actually. So it seems complicated. You need to solve k commodity flow, but it turns out that this can be done fast and deterministic using dynamic shortest path, a k instance of dynamic shortest path. So that is some technical challenge that we can overcome surprisingly by using dynamic algorithm. So now that's the idea. But once you suppose that you have like embed each expander into each part, then there are something more to do, like to embed an expander into the contracted graph, like you contract each of the parts here. But this is now the graph become very small because there are k nodes, and it's kind of easy. Like this is really the key idea. Once you have this idea and try to combine it with previous idea from two previous parts, then you can make it work. But so once you have this, you reduce the Baukat prune to k many calls to cut matching game in smaller graph. Then you can, you know that to solve cut matching game, you can call Baukat prune again, log n times. So you get this recurrent. And you can solve it to be nonlinear by choosing k to be like some subpolynomial term. So to conclude, we do get the deterministic algorithm, which is fast and good quality in nonlinear time, in almost linear time. The idea is to first know that Baukat prune and cut matching game can be reduced to each other, and you resolve a chicken and egg situation by instead try to embed k small expanders simultaneously instead of embedding one large expander. But to embed k small expander, you face one technical challenge of trying to solve k commodity flow. It turns out you can use dynamic algorithm to solve that fast because our flow instance is simple enough. That's the idea. From that, you get a nice application of that resolve major open problem in dynamic graph algorithm and de-randomize a lot of things. One thing that I want to mention is quite interesting is the expander construction that is deterministic and fast. If you have full control, you can choose how to connect one node to another node. There are many ways to construct it. But What we just show here is that you can actually construct the expander even if there are some adversarial, like even if you don't have full control. And this is really the case in the cut matching game, our cut matching game. Our algorithm is both fast and deterministic, even if there is adversary, like even if the adversary chooses a matching, right? Now, one open problem is to improve this annoying interleader 1-2 polylog. As a first step that I think is very interesting, look at this problem. You have a graph. You just need to distinguish whether this graph has no omega-1 sparse cut at all. So it's a great expander. Or it has quite sparse cut, very sparse cut, like 1 over log to the 100 sparse cut. So the gap is like large polylog. Can you distinguish these two cases in m polylog times deterministically? This is not known. It would be great if you can do it. Thanks a lot.